Okay, let's do some examples here. In the first one, it says the shape of the distribution of the time required to get an oil change at a 10-minute oil change facility is unknown. So the shape is unknown. However, records indicate that the mean time for an oil change is 11.4 minutes, and the standard deviation for oil change time is 3.2 minutes. To compute probabilities regarding the sample mean using the normal model, what sample size would be required? Well, this is a perfect example of the central limit theorem. The shape of the distribution is unknown, but that doesn't matter to us because the central limit theorem says as long as the sample size is greater than or equal to 30, then the sampling distribution is approximately normal. So what's the probability that a random sample of 40 oil changes results in a sample mean time of less than 10 minutes? Okay, let's first draw our graph. And the sample mean, remember, sampling distribution mean, sorry, is the same as our population mean. So that's 11.4. We stick it smack in the middle. What about our standard deviation? Well, remember our standard deviation for the distribution, or our standard error of the mean, is going to be the population standard deviation divided by the square root of the sample size, or 3.2 divided by the square root of 40. Now at this point we're going to be a little bit lazy about doing this. We know we need less than 10 minutes, so let's just mark 10 minutes on the graph. And that should be to the left of the mean. And we want less than, so we shade to the left. Okay, so just like we did in the last round of examples for the normal population, to find the probability that the sample mean is less than 10, we do normal CDF. Our lower boundary, since it goes all the way to the left, is negative bunch of nines. The upper boundary is 10. The mean is 11.4. And the standard error is 3.2 divided by square root of 40. So again, if we put that all in the calculator, we have second vers number 2. We have negative, remember to use the negative key, not the subtract key, bunch of nines for the lower. The upper is 10. The mean is 11.4. And the standard deviation is 3.2 divided by the square root of 40. And so we end up with a probability of 0.0028. All right, what happens if the manager agrees to pay each employee a $50 bonus if they meet a certain goal? On a typical Saturday, the oil change facility performs 40 oil changes between 10 a.m. and 12 p.m. Treating that as a random sample, so N is still 40, what mean oil time change would there be a 10% chance of being at or below? And that time that we're about to figure out is the goal established by the manager. So if they do those 40 oil changes less than that, then they get the bonus money. So what we have this time is the exact same thing. We still have the same standard deviation. So our standard deviation, standard error for the mean is still 3.2 over square root of 40. But this time we are trying to find the x bar that we don't know, so that this area left of it is 10%. So remember, when we know the area and we want to find the value that's the boundary, we use inverse norm. And remember, it takes area to the left of what we're looking for, which is 0.10, the mean, which is 11.4, and a standard deviation. But remember, we have a sampling distribution, so our standard deviation, we use the standard error for the mean. So we pull up our calculator again. We go second vers number 3. For area, we put in 0.10. The mean is 11.4. And we're using the standard error of the mean, so 3.2 divided by the square root of 40. So we have 10.75. And that will be the goal established by the manager. Okay, we have a second example here. You should pause the video and try to do it on your own, and then restart the video and see if you got it right. So this one says the length of human pregnancies is approximately normally distributed with a mean of 266 days and a standard deviation of 16 days. So important things to note, it's approximately normal. Part 1 says, what is the probability that a randomly selected pregnancy lasts less than 260 days? Well, this is saying a randomly selected pregnancy. That means only one. So we do that just like we did in the Chapter 7 material. We have a mean, which is 266. We have a standard deviation of 16. And we need that the pregnancy lasts less than 260 days. So here's 260, and we need less than. So the probability, now this time we just use an X because we do not have a sampling distribution. We're only finding the probability of a single pregnancy. So X is less than 260. So as always, we use normal CDF. Lower boundary is negative 6 nines. Upper boundary is 260. The mean is 266. And the standard deviation is 16. And that gives us, when we put it in the calculator, a probability of 0.3538. Okay, moving on to part B. Suppose a random sample of 10 pregnancies is obtained. So now we have a sample of 10 pregnancies. Describe the sampling distribution of the sample mean length of human pregnancies. So we need to go see if we have any underlying information about the underlying population. And they said that the underlying population was normally distributed. So since the length of human pregnancies is normally distributed, the mean length, we should say the sampling distribution, the sampling distribution of the mean length of human pregnancies is normally distributed regardless of the sample size. Okay, now let's figure out the probability that a random sample of 5 pregnancies has a mean gestation period of 260 days or less. So we have the mean for the sampling distribution. That's always the same as the mean for the population. And our standard error of the mean, remembers the standard deviation for the population, divided by the square root of the sample size. And we want less than 260 days again, so 260 to the left. So the probability that the sample mean is less than 260 is, again, it's just a normal CDF. And we are going to use -6/9 for the lower boundary because it goes to -infinity. 260 is the upper bound. 266 as the mean. And we now have a sampling distribution, so we use the standard error of the mean for the standard deviation. When we put that in, we get approximately 0.2009 for the probability. Should go back to part B and say that that sampling distribution will have a mean of 266 and a standard error of the mean of 16 over the square root of 10 for that. Sorry. All right, we'll finish this problem in the next video.